Questions? The attendance register is being passed around. Yep. Just as a little refresher, right? We talked about graphs last time. Get your memories. Actually, it wasn't very long ago. It was just 3 days ago. So everybody, I'm sure this is still fresh in everybody's mind. And today we're going to talk about n-dimensional data. To make you as confused as possible, these terms may not be considered exactly identical, but they're generally used in a kind of interchangeable way. N-dimensional data is also called multivariate data, is also called high-dimensional data. Some people might make a distinction between these two, being multivariate is 5 and less, and high-dimensional is 6 and up. But generally speaking, these terms are used interchangeably. Maybe that will change someday, but that's the way it is these days. So I think everybody is familiar already with scatterplots. You can use scatterplots in assignment 1. Generally, we're looking for visual designs that can encode 3 variables or more. Like, how do you represent 3 or more variables? Is it possible to represent 10 variables at the same time, for example? Like, is there a good way to do that? And this scatter plot, anybody want to tell me how many variables are being represented on this scatter plot? 3, yeah, I forgot I have the answer on the slide. There's weight on the x-axis, there's average size on the y-axis, and then color encodes another thing, the horsepower. This is a data set of cars, so to speak, if you didn't deduce that already. So as the weight goes up, so does the average size of the car. And, well, we can't say, the horsepower, we can't say kind of does increase. As the weight goes up and the average size goes up, the horsepower also increases. But it's not that obvious. The weight and the average is kind of obvious, but the horsepower is not very obvious, right? We can take the idea of one scatter plot and then create a scatterplot matrix. So combining a number of scatter plots together. So this is a 3 by 3 matrix of scatter plots. And 3 variables are plotted on both the x alignment of the matrix and the y axis of the matrix. So retail price appears twice, here on the x-axis and here on the y-axis. And that's not very interesting, right? Because it's just this, it just creates a line down the middle. But here we have average size versus retail price, right? So there's a funky car that's very, very expensive there, right? And it has an average size. And now we have horsepower plotted against retail price. And so we have redundant information here. Retail price plotted against average size, but that's here also, but the axes are flipped, and so on. This is average size against average size, horsepower against average size, and so on, so that's also redundant. Right? And then we have horsepower versus retail price. Horsepower versus average size, and horsepower versus horsepower. Question in the back?
How often is this useful, considering that you're trying to show 3 scatterplots?
What's
So
your
you
name?
only care about average size versus price versus horsepower, and horsepower versus size. Sure.
What is your name? Hamel. Very good question. Is this useful? Was that the question? Or how is this useful?
the amount of redundant data you have, especially stuff with themselves, you have three useful graphs, and then the rest are not particularly.
That's true. There's a lot of redundancy there. It's true, and so really you could immediately delete half of them, and it wouldn't do much harm. And probably you could delete these extras. You can also imagine this being like bigger, like 4 by 4 or 5 by 5, and it's just a naive way of trying to depict n-dimensional data. It's like if you had to try something naive, you know, this is just one of the possibilities. And a lot of people do this. You find this is not very uncommon. So it's useful, but it has limitations. So it's a double-edged sword. You could just, like I said, delete the redundant scatter plots. But the limitation, can anybody speculate what the real limitation is there, besides the redundancy? Carlo? Size. Yeah, the size, right? The number of variants is only 3 here. So as soon as we start to go to 4, 5, or what about 10, then the plots are going to become really, really small. Right? So it's not very scalable. But there are better techniques for scalability, but I wouldn't say that scalability is a solved problem completely. There are solutions, but I wouldn't label it as a solved problem. This is another version of the Scatterplot-Matrix, but with details on demand. So you can rearrange the columns and the rows interactively at the top there, in the matrix. You still have those redundancies, but now you can click on any data sample and then get the exact data that it corresponds to, the underlying data. Right? So this is somebody clicked on the Honda Inside 2DR, so that one is very strange, right? This car is very unusual. It's always at the borders, right? So it gets, well, it's really strange because it gets the highest miles per gallon, right? That's one of the things that makes it very strange. And yeah, it's the most efficient car by far in the graph. Here's a 3-dimensional, so to speak, example of scatter plots. So there are 3 axes. There's the engine size on one axis, the miles per gallon on another axis, and then there's another axis there, engine size. That's not so easy to read. Actually, city, okay, that's horsepower. That's horsepower. And you can rotate that around. Color's not being used. So this requires that you're able to rotate the cube. Otherwise, it's going to be very difficult to see that 3rd dimension. You could add color there as well, to add a fourth dimension. Can anybody think of a way to add a 5th variable or a 5th dimension to after color? Any other options? Size. Could vary the size of the ellipses. Any other options?
Shape.
Shape, exactly. Well done. Yes. Any other options?
Like slider for time.
Well done. What's your name? Liam. I think you have psychic powers. Actually, I was thinking about that, and I think you picked up the signal. Or vice versa. But that is correct. You could add animation or an interactive widget that represents time. Right? And the data samples move with time steps. And shape could be varied as well. There is another one, if anyone is feeling really psychic, or psychotic. I would be surprised. You could also vary, I'm not saying these are all necessarily a good idea, I'm just saying they're possible. You could vary the opacity of the data samples, so some of them are more transparent than others. I'm not saying it's going to turn out really great, but it is a possibility. Right? Here's another possibility, a stacked bar chart. So every bar represents a variant, right? And then they're stacked on top of each other. In this example, we are looking at the state of higher education in Wales. So what is being taught in Wales in higher education institutes? This is something that the Welsh government and Swansea University would like to know. Like, what are people studying in Wales and where are they studying those subjects?
Not much of Royal Welsh
Well, that's very, very specific. So I don't know if music is in that list. Okay, music doesn't seem to be in this particular list of variants. But that you get some idea of you know, it's a possibility. It's a possibility of a multivariate visual design. It doesn't mean it's the best, but it is a possibility, and it would be okay for assignment 1 as well. An area graph is another possibility. This is the same information, I believe. Right? Each area represents one variant, and then the institutions are plotted along the x-axis. Right? This one's already outdated. And so they're stacked in order of the same order. There should be a correspondence between this order and this order. And if there are too many bands, then it does get confusing, and you can see that there are lots of very thin ones up there, so it's very... But if there are only like 4 areas or 4 variants, it works better. Right? But this is another attempt at trying to visualize multivariate data. It is also fine for assignment 1 if you want to use an area graph or a stacked graph. Matrix chart is another one. So we have the x-axis, the institute. The y-axis separates the type of student, postgraduate and undergraduate, and then the color encodes subject matter, and the size or the radius is redundant in some ways, but it encodes the number of those students. So here's undergraduate, here's postgraduate. So it would be nice to see. This is also a little bit outdated, but anyways, Cardiff has the most postgraduates, right? But probably they have the most undergraduates too. So it's another possibility. It's a little outdated. It would be interesting to see what it looks like in 2018 or 2017. So those are some very generic multivariate viz techniques. Now we're going to go into some more of them, but they're a little bit more specialized. So we're going to talk about glyphs now, which are another multivariate visualization technique. Unless there are questions before we move on. Now, I'm including this example. Nobody knows if this is like a serious example or not a serious example, but whether or not it's serious or not serious, it is very famous and it's highly cited, and it's always included in data visualization books. This is one of the first glyph-based techniques for high-dimensional data. So it's a scatter plot, right? There's an x-axis and a y-axis. So there are 2 variants encoded by just the position of each glyph. But then the shape of the faces also encodes the other information. The head, the shape of the head encodes a variate, right? These heads are different shapes. Some are round and some are not round. And the size could include another variate. Here they're pretty much uniform size, but they could include another variate. The mouth length is changing. Some people have a long mouth and some have a very short mouth. And the curvature is also changing of the mouths, right? So this one is kind of straight and maybe this one has more curvature. That one's straight. The eye's shape is changing. It's not easy to see actually, but the shape of the eyes is changing if I compare those eyes. And the size of the eyes is also changing, right? Color is absent from this example, but it could be used to encode a variance. And I looked up this paper. I actually downloaded it. I don't know if I put it on Blackboard or not. I might have. Just to see, like, is this real? Like, is this serious? It's published from I believe 1973. Yes, in the American Journal of Statistics, something like that. And the way they used it was to encode fossil specimens. Somebody had collected hundreds or thousands of fossil specimens and they were trying to study them. And I couldn't make heads or tails out of it, actually. I looked at the examples and I couldn't deduce anything about the fossils from these. But anyways, they're highly cited, always included, and arguably not very useful. We're going to talk about these a little bit more, but these are another type of glyph. They're called star glyphs. Every axis in a star glyph represents a variant. And then the polylines join the axes for every data item. So for every item we're trying to represent, it's represented by a polyline that connects the axes together. And then those star glyphs form different shapes. Right? We're going to talk about this in a little bit more detail coming up soon. You've already seen vector glyphs, but just to make it clear, these are trying to depict 7 variants at the same time. So they all have an x, y, z position. That's 3. Then the velocity has an x, y, and z component. That's 6. And then there's color, which represents magnitude. Well, there's size and color redundantly encoded. Right? The size of these is changing. Right? So is the color. So there are 7 variants being encoded there. We can modify those a little bit and try to add some more information, right? Like an extra one, 8th variable, right? Well, we have x, y, and z position, velocity, magnitude, and then angle range. The angle range is represented by this extra piece around the glyph, this ring. And then the radius of that ring is increasing or decreasing depending on the range of angles represented by that glyph. Right? This glyph is pointing in a direction, but then it represents this cluster of glyphs, and inside the cluster you find that range of angles from the average. It's just some examples of how can we try to represent 8 variants, for example, at the same time. Here's another example, very similar. Right? The arrow direction is replaced by magnitude only. So we have the x, y, z position. We have the velocity range, the magnitude range. So this is the minimum velocity, and this is the maximum velocity magnitude. Right? And then we have the color as well. So we have 6 variants represented at the same time. And this is trying to combine them to get 9 variables all at the same time. I think we saw this example already. Anybody here watch rugby? Anybody else? There was some big game, wasn't it, in Swansea play like a few days ago?
Six Nations play.
Mm-hmm. So what's the big challenge? What's the big challenge for rugby coaches and players and analysts and trainers? What is the big challenge for them?
They easily not win the wooden score again.
To avoid embarrassment.
That's a massive challenge.
So the goal of rugby is to beat the opponent, right? So that's a big challenge. That's pretty obvious. So if you want to beat your opponent, you want to study their game strategy. Right? That's true about any sport. Is that a challenge? Can anybody imagine that being a challenge? Like trying to study an opponent and come up with a winning strategy? What is the challenge there? Why is that so difficult? Anybody
You have
have?
a lot of moving pieces at the same time.
You have a lot of moving pieces at the same time, definitely. Yes, a lot of data, so to speak.
Each one is independent.
Each one could be independent. Any other challenges?
To read a single set of data, you're going to presumably take an hour or hour and a half to watch the entire game.
Exactly. You are awake today and you're blowing me away. Yes, so it's the time. Imagine you are a trainer and you have to figure out the opponent. You would sit down, right, with a notepad, I guess, and a pencil, and you'd press play on your video or DVD recorder or whatever, your MP4 player or whatever, and you'd watch the opponent's games, right? That's what you would do, and that's what people do. And that takes a long time, just one game, maybe take 90 minutes or something like that. And if you want to watch 2, 3, or 4, and then if you want to study multiple opponents, very, very difficult. And also imagine if you see something that you think is interesting in one game, and then you're watching like 3 games later, trying to make the connection between events in the first game that you watched maybe the day before, and then trying to make that connection like, oh, didn't I see that pattern like 2 days ago or 2 games ago? Where was it again? And like trying to find it, fast forward and rewind. Very, very difficult. Very, very difficult. So this is a glyph that represents every event in a rugby game, right? It tries to summarize every single event in a rugby game. Because there are people sitting on the sidelines, and whenever there is an event, they record all these properties about the event, like who was involved, how far down the field did they get. So they encode like the time at which the event happened, how long the event took during the game. The tortuosity is not something they record, but that's something that can be derived. Anybody ever heard of tortuosity? It's a pretty cool word. It sounds like torture. Carlo, do you know what it is?
I used to describe roads that are very...
Yeah, how did you know that?
Huh?
How did you know that?
It's Latin.
Oh, okay, good. That's very good. So yes, you can use it to describe the amount of curvature. In this case, it's the amount of curvature that a player ran as they grabbed the ball and tried to score. The territory start position, right where you start the play. The team is encoded in the net lateral movement, so the amount of back and forth laterally rather than towards the goal. Right? The phase number is encoded, the direction of the play is encoded in the direction of this arrow. The type of play is encoded as a pictogram, and then the amount of gain is mapped to the color or the inner color. right? That's sort of what it looks like if you, this is the way the glyph changes depending on which variant you're looking at, right? This is negative gain, meaning you're going backwards, and this is what major gain looks like, so it's mapped to this color. These are the different events: kick receptions, lineouts, turnovers, scrums, penalties, and so on. This is the territory start position. This is how that's encoded. It's encoded by the thickness of this ring. This is what low tortuosity looks like and high tortuosity, and so on, like the number of phases. And direction, net lateral movement, time, and phase duration are all encoded in that glyph. So lots of variables, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's what a game looks like. So you can map all the events onto a scatter plot and get the overview of the game in just a few seconds. In this particular example of the screenshot, time is mapped to the x-axis, so the starting time of the game, ending time of the game. You can see the halftime. And then gain is mapped to the y-axis. So you can see right away for this purple halo, it encodes tries. That means a team has scored points. Right, so you can see this sort of nobody scored any points in the later part of the game. And the points are not always associated with, for example, high gain. In fact, the points are associated with some average gain. And there's a YouTube video about that. If you want to see that in more detail, there are a few YouTube videos about that in more detail on the DataViz YouTube channel. If you want to see it in greater detail, and the user playing with the software and showing different features and the way the interaction works and so on. If we have time, maybe we'll show that. And you can compare matches with each other, right? These are two different matches, and you can compare their behaviors and the repeat events in the two matches. Right, this one, there are lots of tries. You can see, for example, there are lots of tries in every phase of in the different games. And for each event, in this case, the x-axis is sorted by event. So events are associated, tries are associated with every type of event. In this game, the full spectrum. But in this game, tries are only associated with lineouts and scrums. So the behaviors of the games is very, very different, and you can see that immediately, right? Just from a few seconds, you can get an overview of the game. Well, does that work? Yeah, it does. So that's a full 36-minute presentation on just the rugby stuff, on just the rugby visualization stuff. So you're welcome to have a look at it if you're curious. And then the original rugby demo videos are also on the YouTube channel. You get a lot of bang for your buck in this module, don't you? Okay, has anybody heard of parallel coordinates before? Anybody ever heard of those? No? Nobody's heard of those? Okay, good. Good. I guess we'll give a quick, before I jump in, maybe we end with a quick demo, or since I have the whiteboard and the marker, I will give a demo of that. how to construct parallel coordinates. Before I draw it though, each axis here represents a variate, right? In this example there are 1, 2, 3, 4, 5, 6, 7 variates. And for every sample in the data set or data tuple, it's connected by a polyline. And here it's hard to, there's lots of line crossings. But this is a high dimensional visualization technique. So 1, 2, 3, 4, 5, 6, 7. In this particular case, it's a 7-dimensional visualization technique. And to make sense of that, I will draw it by hand.
Isn't that the same along the glyph?
The same as a glyph?
Yeah, like if you open the glyph and you put it side by side, look at the same.
I wouldn't say that. I wouldn't say that. Let's see how that's constructed. So I think I need to turn that off.